But what's relevant is that the magnetic field that's produced by this by the electric movement of charge. And even though the net charge is zero, you do have all of this drift, right? These electric charges. The actual magnetic field is oriented at a 90-degree angle with respect to the direction of the current. And the manifestation of the magnetic field, this is coming out of the board and this is going into the board. Spirals around the movement of the charge. So if I've got a charge moving, or a flow of charge, say in the direction of my thumb, the way my hand, the way my fingers curl around my thumb, is the direction of the magnetic field at any point around the wire. So if I've got a current carrying wire pointing in this direction, if I take my fingers and curl them at the top, it implies that I drew this horribly. I drew it in a plane. I didn't mean to. I'm trying to make it. That's a little better. Oh, it's hard to do this for me. Something like that. At the top, the current comes out of the board. And all my fingers around. If the tip of my pen is the direction of the field, it will rotate in a circle around the wire and then come up the back side. So it's a 90-degree, it basically rotates in the plane normal to the current. The magnitude of the current then, the magnitude of the magnetic field, as with most fields, changes. It gets weaker the further away you get from the source that produces it. Right? It's not going to increase the further away you get. It's always going to diminish or decrease. And it turns out that for a wire, at least for a long straight wire, the magnetic field ends up being related to the current through the wire, inversely related to the distance away from the wire perpendicularly, and a factor of 2 pi divided into some constant we call mu. And we'll talk about what those things mean. I have a copy of the lab. So, let me erase some of this stuff and sort of clarify some of these things. Okay, so to begin with, mu for magnetic fields is the fundamental constant in the same way that epsilon naught is the fundamental constant for electric fields. It has a value of 4 pi times 10 to the negative 7th, I believe. And the units are Tesla meters per ampere, where B is measured in Tesla. So magnetic field has units we call Tesla units. And we'll talk more specifically about what they mean. It's like the really bad hair band in the 80s. God, or 90s, I hated it. I don't know why. I always wanted to like them, but I could never stand more than the first song of the album they ever made.
You want to jump on that bandwagon?
Yeah, I used to call them Pugler. I just couldn't stand it. Okay. So this is the permeability, not permittivity, but permeability constant in vacuum. It's got a strange number. We'll see why this number comes out the way it comes out. It's basically what? 1.27 times 10 to the negative sixth as an actual number. But we express it in terms of units of pi because those units of pi oftentimes cancel out with certain configurations, with certain geometries. So, and of course, I is in amperes, and R is separation distance. So this is a basic expression. As long as you have a wire that's relatively long compared to the distances that you're measuring, it looks something like this. Now, again, what's interesting about it is whatever the direction of the flow of the charge, the observed magnetic field will always be 90 degrees to that. Do you remember? Oh, what would be a good example? Oh, in chemistry, electrons. When they talk about spin up and spin down, you know what those refer to? Those quantities, those conceptually, what those ideas really mean? Well, it's the magnetic moment, just like a dielectric moment. So for electrons, in chemistry, if you will, we talk about an electron having a spin up or a spin down. And what this basically means is that you think about an electron as a little magnet, and that little magnet has a north and a south pole. And as a magnet, the magnetic field would kind of extend and ultimately terminate back at the butt of that little magnet. And the opposite would be true for a spin-down electron. Now, these are just relative to each other. There's no real spin up or spin down. It's just one's relative or opposite the other. So we just start with the reference of one. But here's the thing. What we visualize, you probably talked about this in chemistry, is an electron spinning like a little top. Well, if this is the direction of the magnetic moment, or what the magnet looks like, if you will. It's like a little bar magnet. It's like the electron is spinning. Take your thumb, it's like it's spinning in a circle. And as it spins like a top, it produces a magnetic field that has a north end and a south end. So again, moving charge. Because you can spin just as easily or just as equivalently as you can move in space, right? Rotation, translation, they're just two different types of motion. So when you have electrons spinning in a certain way, you produce a magnetic field that points in the direction of your thumb, which is kind of backwards, relative to the spin occurring in this plane. But again, it's the same thing. If you've got a current moving in a circle, then the magnetic field is going to be 90 degrees with respect to that plane. So we've seen this before. Then the reverse would be true. Well, if you had chemistry, you've seen it before. So this is essentially the idea. Charges can move, and as they move, if they move in a straight line, like an electric field, you see electric current. If you see it moving rotationally, you see it as essentially the equivalent in an electron of the spin-up, spin-down phenomenon, which is necessary because a negative attracts to a positive, or I'm sorry, a north attracts to a south like a magnet, and the magnets essentially will want to stack together like two side-by-side bar magnets with their poles opposing. And that is an attractive relationship which helps counteract the repulsion of their electric charges that they carry because of their electrostatic, because of the sign of their charges. So there's all kinds of this logic building up. How do you get attraction when you have repulsion? And this is one way that it happens, and it's directly observable, and we see a lot of different features of this. So that's essentially the idea. Now, so we got two different ways electric charge can be produced. Or I'm sorry, magnetic fields can be produced from electric charge. Think about what would happen if you stack a bunch of these magnets together, a bunch of these little circular magnets together. So I'll take one, it's an electron, but it doesn't have to be an electron. What if I took a bunch of these electrons with the same spin and stacked them on top of each other? Each one has a north-south. The north attracts to the south of its vertical neighbor, north to south, north to south, and you end up with a stacked, if you will, combinational or combined magnet. It's like taking a bunch of those little ceramic magnets, and when you stack them all up, you get more magnetic field just by stacking the magnets up. I'll find some of those and show you that. I don't want to do it this second. Well, this relationship can be approximated and observed. This is the equivalent of each of these has the same amount of electric charge. As those charges are moving, this is no different than having a coil of wire, if you will, with charge flowing through it, because the charge will spiral, and as long as the stacks or the loops, the coils of the wire are close enough together, then it's kind of like just having electrons stacking on top of each other, if you will. So this is a wire carrying or current carrying wire solenoid. And we're going to focus on this one today. And again, what you end up with is essentially what looks like a little bar magnet, as long as you stay close, which will have a magnetic field that runs up the shaft, if you will, in the middle of this coil. And that's why we have this linkage. We're going to actually observe and look at the effects of varying the spacing and the quantity of electric charge that passes through this, this spiral conductor. That's the basis of an electromagnet. Those electromagnets you see for like picking up cars, essentially all they are is some big coil that's designed in such a way that you get a huge magnetic field, like a big old bar magnet. And so that bar magnet comes down, grabs a car, and lifts the whole damn thing up. So we're going to use this relationship to do two things. And again, I want you to think about the relationship fundamentally to what might be essentially stacking up a bunch of spinning electrons. Because it's the equivalent idea, if you will. Now, here's the thing. When you have a solenoid like this, the magnetic field in the solenoid and the magnitude of it is directly proportional to the amount of current that's flowing through it, right? Because that would basically be the same thing as the amount of charge that's spinning in a circle, if you will. Kind of like with electrons, it would be related to the number of magnets or the number of electrons, spinning electrons you stacked on top of each other. If you will, the number of coils. If each of these is a coil, you've got N of them. Inversely related to how those coils are spaced, the further they're spaced, the weaker their interaction, and the weaker the vectors add together, right? So the further away you get from an individual coil, there's your electron, if you will, the further away you get, the weaker the field is that will interact at this point here, even if you put another electron there. But you bring it closer, or you bring the coil closer, if you will, you get a stronger magnetic field, you get a stronger additive response. So it's inversely related to the separation distance. Or what we say, if this thing has a certain length of L, then we say it's inversely related for a coil to just the length of the coil. Because that's related to the coil spacing, if you will. And then, of course, we have this constant, mu0 built in here. Now, here's one of the most fabulous things about this experiment. It's relatively simple. We haven't talked a lot about the next two chapters, so we've got a little bit of, we're stepping ahead a little bit. But think about this for a second. what this tells you is, say you have a slinky with some number of coils. Say N coils is 100. And the length of the slinky then depends on how it's stretched. And say it has a current of 1 ampere passing through it. If I plotted the magnetic field as a function of how far or how much I stretch those coils out, if I measure B
So we need to call
as
how many
L
coils that we have?
varies,
I guess so.
so here's my
Or
slinky,
more like the length of the coil.
and this might be L1, and I measure the magnetic field here. And then I stretch it out, so it's now a new length, and I measure the magnetic field in it. And then I do the same thing for a bunch of different coil lengths. As the coil increases, B decreases. So this thing ought to look something like this. So B, if we were to plot it this way, as a function of L, say in a curve fit form, would be related to some fit constant divided by the various lengths. And I'm going to put some y-intercept in here. Call it C, I guess. Because this thing may not line up perfectly at 0. Depending on how it's zeroed, you may have something else going on. So we would expect a relationship that would look something like this. And we're not going to plot it quite this way. But if we did, and we fit this thing to a curve that was an inverse curve like this, what would we expect mu A fit to be? What would correspond physically to this fit constant A fit? What would A fit represent?
Times I times the number of coils.
Well, if I'm plotting this versus this, it should be I times N times mu. So A fit should represent mu N coil I. And if I knew N and I, mu naught should be related to A fit over the number of coils that are spread out with this current I passing through it. Okay, so this is functionally the idea. We're going to vary the physical parameter of L, and we're going to use it and develop and get a curve fit and use that curve fit to calculate this permeability constant. So it's just a magnetic experiment, circuits and wires, and we're somehow measure a magnetic field, and we're going to get this mu value. Okay? Doesn't seem like much. Now, another way to approach the problem, and this is how the lab physically does it, these type of fits are always chock full of these weird experimental errors because it's a nonlinear fit. A better way to measure it, this is how the lab does it, how it's expressed in the lab, rather than deal with a fit like this, we're going to do a calculation of the number of coils per length. So we got the same slinky, we got the same number of coils. We're going to measure the number of coils at a particular length, and as we vary the length, then we're going to calculate the ratio of the coils to that new length. So a better plot, hopefully, is a linear plot. If we plot B now instead as a function of the number of coils per unit length, what would we expect this graph to look like? As L decreases, N over L increases. This curve should look like this, the slope of which should give you something interesting. So BL is now related to some fit slope times N over L plus some fit constant B, or y-intercept. What would the slope represent? What would be the significance of the slope? It should still be mu naught times I. No N now, but just mu naught times I. So if I took that linear slope and divided it by the amount of current, guess what? I ought to be able to get mu naught.
Just for your notes, you want B to be of N over L.
I shouldn't call this B. What's that?
The B in the beginning of that equation, you want it to be
N
of
over L. Yes, you're right. Thank you. I better call this C fit again. I don't want any of that. B's all over the place. So again, we can calculate mu from this. We take M fit, and all we have to do now would be to divide it by I, if we keep the correct constant. So that's one way to calculate this mu naught. And it's very direct. It's a lot easier than trying to calculate epsilon naught. We never directly calculated epsilon naught, did we? We calculated the dielectric constant. Why didn't we calculate epsilon naught? Any idea why I didn't just have that built into the lab somewhere? There's a real good reason. No. You separate two plates with air in between. What's the problem with that?
Air is a dielectric.
There's a dielectric, so it should have a dielectric constant of 1. So we should be able to use a parallel plate capacitor and have it separated by air. The problem is, it's kind of hard to get a uniform spacing when you've just got two flat plates with nothing in between them. You'd have to put rubber spacing or something which would change the effective dielectric constant. So it's just, as a practical matter, difficult unless you put something physical in there. But the nice thing about magnetic fields is that you don't have to do that. So there's some amazing advantages to it. So we didn't calculate epsilon naught, but we can directly calculate mu. Okay, so how else can we vary, what else could we do to manipulate this relationship? What else could I do with this thing that might be a practical way of designing an experiment to maybe calculate mu naught?
Change the current.
Change the current. That's usually the easiest thing, right? You got the knob. So alternatively, we could say that B is related to mu naught N coil. I'm just re-expressing it over L times I. So I just rearrange it this way. So it's a little bit easier to see. So if I performed an experiment where I varied I with my measurements of B, I should be able to get a graph related to those quantities. As you vary the amount of current, what happens to the magnetic field? Well, if this relationship is any way at all accurate or reasonable, this should look like a straight line. As you increase the current, the magnetic field ought to increase. And we ought to be able to fit this thing to some slope, or I'm sorry, to B as a function of I should be related to some m fit times I plus some y-intercept. And the y-intercept is always just to make sure that this thing stays straight and true to the trend and not just fixed and forced through the 0 point, which is always what happens when you don't have a y-intercept. Because then the assumption is with most equations you get with this, you assume that there's no offset in any of your data. this case, what would M fit be related to?
Music.
Mu naught M coil over it.
U naught M coil. Easy thing to measure, divided by the length that you used when you did all these varying current measurements. From this, we should be able to get mu naught. So we're going to use two similar types of experiment, but two different manipulations of independent variable to get an estimate of mu naught. Now, I want you to think about this one for a second. Aside from the technical difficulties with it, if we had a way of keeping two conducting plates perfectly parallel, and we're able to measure their distance of separation as you brought them closer together in air, then we could have directly measured or estimated epsilon naught. It's a fairly straightforward measurement, right? Just like we did in the second lab, the capacitor lab, second lab, third lab. But think about this now. So it's a direct epsilon naught related to electric fields is a directly lab measurable quantity. In the same way, so is mu naught. Now, here's an interesting thing. I think it's interesting. I study physicists, so I guess it is. I also been a lifelong New England Patriots football fan, so that tells you everything you need to know.
You sport that. At least you gotta run in that farm.
Anyway,
From Oregon. We got, what?
no, they just dropped him.
Did they drop it?
Yeah.
I wondered.
Yeah, last year. We did think him. Yeah, I think they just cut him.
Still got Tom Brady.
So, oh, he's got Tom. Oh, he's got Tom. Okay, so what is what I want you to do? I want you to take mu naught and epsilon naught and calculate the number and take the inverse of it. Do it. Okay, so you know what mu naught is?
This is
Well,
gonna be the giveaway.
8.85 times 10 to the negative 12, and the units are Coulomb squared, Newton meters
No.
squared. Mu naught has units of 4 pi times 10 to the negative 7th. And the units would be Tesla meters per ampere. And I'm going to go ahead and tell you that a Tesla the unit of a Tesla is a Newton. Second, per Coulomb. Meter. I think those are the units of a
We're
Tesla.
just getting data
Okay.
today, and we're getting the fuck out of here. That's it. That's incredible.
It's raining again. I can't believe it.
Yeah, I wasn't expecting rain.
I wish it rained more.
When you do this calculation, what do you get for a number?
About 9 times 10 to the 16.
9 times 10 to the 16th. And what are the units? If you put all these units together, what do you get? Seconds squared per meter squared. Right? You got seconds in the denominator, and you got another seconds in the denominator. You got a meter here. This meter cancels out with that meter. You're left with a kilogram meter per second squared. That cancels out with that. The coulombs cancel out. And you're left with this. Now, is that right? Am I losing something out here? The coulombs cancel out. It's a missing coulomb somewhere here, it seems like.
Fried it. Slinky.
No, this I think is okay.
I want that you to fit 100.
Oh, we got the ampere, sorry. Yeah, seconds, the Coulomb cancel out from the
I want
ampere
my
per second, or Coulomb per second.
Slinky to launch projectile.
Okay, here's what I want you to do now. Yeah, this is just esoteric. I don't know,
Flame
9 times 10 to the
projectiles.
16. It's kind of like, I don't know, 1 over
Think about it.
E or something, right?
If we
Here's what I
decide
want
what
you to
we
do.
make
Take the
it feel
square root
right.
of this.
But if we take it to contain
What
it
do you get?
to a cylinder,
You got it.
then we take some kind of material, then metal material.
Yeah.
With the
Can we-
there.
And the units would be,
Should
you
we do
take
the
the
magnetic
inverse
field?
of this.
Well,
Oh, this is
as far as you two
meter
do,
squared
the
per
same. We
second
can
squared.
throw it
I'm
in the
thinking
middle,
of
and then it'll
There
float,
we
and
go.
then it'll
You
melt.
end up
No,
getting
I don't want it to
the speed
float.
of
I want
light.
it to shoot. I want it to.
Well, you know, okay,
From the
so
floating, we
why
can
is this interesting? This is not a live experiment. There's absolutely not a damn thing to do with light in anything that we're doing today, or in anything we've done up to this point in this class. Yet somehow, ironically, the physical constants that either we measured or could have measured by the end of today can be combined in a very simple way to predict what the speed of light should be, based on the measurement of these constants. So now think about some illiterate printmaker apprentice toiling away for 20 years making measurements of magnetism and electricity and coming up with these physical constants just by direct measurement. You may have heard a guy, his name was Faraday. And then a mathematician comes along and he's looking at something kind of based on this, but he generalizes these ideas, takes some work people have done in other areas, and he notices that if you take these two constants and you just arrange them this way, I don't know why some guy would even bother doing that, but just start taking some electrical magnetic constants, since the charges are related, whether there's motion or not, you just sort of piece them together and somehow you get the speed, something close to the speed of light. Maybe light is related to electricity and magnetism. Maybe the phenomenon is an electromagnetic phenomenon. Okay? That was a keystone moment in science. One of the coolest and most amazing moments of inspiration. I mean, think about that. That's the equivalent of pissing in a bucket, measuring the volume, and somehow coming up with the equivalent to black holes or something, right? It's just, they're so disparate, they're not even related, right? Take measurements of a table and somehow that's related to, I don't know, electric field or something in a quantum state. I don't know. I mean, it's just, there was no reason why they had to necessarily be related. It wasn't what they were looking for. It just happened. Kind of like heat and work, if you will. Maybe that's the best correlation.